So today we want to review October 13th. We want to review the first 3 chapters because we want to have a test next week. And so I'm just going to go through the chapters here and pick out some reasonable questions. And it might also be sort of useful to kind of see where we've gone so far. So what is universal automatism? And that's simply the idea that every process, everything in the universe could be a computation. One thing I didn't make clear right off in the book that now in retrospect I wish I had. Sometimes people say, does this mean there's one single computation that's everything? Like if you run like Grand Theft Auto, or there's like you buy this one CD and that's the one program, you put that in and that's the whole program, that whole world is that one computation. But I would be inclined to say that it might be that there's lots of different computations in our world, rather than there just being one of them. Now, does there have to be one underlying thing? Well, we talked about that a little bit earlier. That gets into the monism, pluralism thing. I mean, does the universe have to be one thing, or maybe it's a lot of things? So I would say the universe is made of computations, but there might be lots of them. One other issue that comes up in this connection is another thing I forgot to put in the book, which is that computations can exist at different size scales. Like if you say everything's just atoms, that's like one kind of small thing. But we can think of large-scale things being computations. And if what I'm saying doesn't seem reasonable, feel free to interrupt. The other thing, the next question would be, what is a computation? So what's how am I defining computation for my particular devious purposes in this book? And if I want to say that everything's a computation, then I want to be very generous about, I don't want to make it very tight. I want to make it pretty easy for something to be a computation, because otherwise I'm going to have a problem. So I don't want to just say a computation is a Turing machine or something like that. So what I ended up saying in the book was, let's see if I can remember this. I think I said a computation, a process that obeys a finitely describable process, deterministic. Let's see, how did I say it exactly? This would be on page...
Process that obeys finitely described rules.
Yeah, that's it. So computation is a process that obeys finitely describable rules. And hidden inside that is, if it obeys, then you're also saying the process is deterministic. But I didn't bother putting that explicitly because it seemed more elegant to have a really concise definition. Finitely describable, that's important because if you allow an infinite description, well, anything in the world has an infinite description. I mean, you can take something completely random, and then the description is that infinite list of things that it does. So, and the idea of rules, that's sort of our notion of computation is you have a program, and it unfolds from that. Okay. Third thing, what is the dialectic triad? In the book's title. In other words, why is the book called what it is? And that's, again, these are pretty easy questions. It's, on the one hand, the life box is this idea that, I'm going to talk about life box more in chapter 4, but informally I've already described it as being this idea of getting a computer model of yourself, something that can answer every possible question the same way as you. And there's this dream which hasn't happened yet, and it might not happen for another 100 years, but it seems in principle that it will eventually happen, that we can write AI programs. Or maybe we can't write them, we can evolve AI programs, or they can come into existence, which would think more or less like a person thinks. And so then the full life box would be something with all your data, and it's got this AI program that puts things together pretty much the way that you would put them together. And so then you say, well, is that the same as me? That's the thesis. The antithesis is, what about my soul? I've got a soul, I'm me, I've got this glowing sense of self. That doesn't seem to be captured by the idea of a mere computation. And then the synthesis is the one that I put in the middle, and that's the seashell. And seashell is being used here as sort of a code word. What it really stands for is the idea of a gnarly computation. And the reason I use seashell to mean that is because of Stephen Wolfram has this sort of mascot for his whole view of cellular automata is our friend the textile cone shell, and which has a pattern that is somewhat like Rule 30 or Rule 110, which are the simple CA rules that generate unpredictable, complicated stuff from a very simple start, obeying rules. Okay. Now, Section 2 of Chapter 1, A New Kind of Science, the big notion that we get into there is the idea of being unpredictable. Okay, so what does it mean to say, well, there's sort of two steps. What does it mean to say, well, let's say a computation is unpredictable. Let's say computation P is unpredictable. And this is, actually the definition of this is somewhat technical. Intuitively, basically the idea is there's no rapid shortcut computation for predicting P. And the reason I say it's a little technical is that to really unfold what I mean by shortcut, we kind of need the idea of emulation. So we could kind of throw in another question. What does it mean to say that, so let's just put a ditto here. What does it mean to say that Q emulates P? And the idea is computation Q emulates P. There's various ways to define it. And if you go and look in the technical appendix, I even get into, there's 2 or 3 alternate ways to define it. But one kind of simple way that'll do for now is to say that there's some kind of code. We could say codes of P, so that Q of codes of P in produces, or let's say terminates in some state out, is equivalent to saying that P with some input in terminates in the same state out. So the idea is we say that Q emulates P if there's some code, so that I drop that code into the Q computation, I give it any input, and then it'll imitate the behavior of P and produce the same output that I would have gotten if I had just dropped that input into P. You look a little dubious, Ephraim.
No, it's in another class here studying homeomorphisms.
Uh-huh.
So,
It's like a homeomorphism, yeah. It's very simple. And when you look, the full, more accurate definition of this is even more like a homeomorphism, because that I've given the technical appendix. Because it might be that, maybe this might be water in a basin, and this might be the stock market. In that case, the input to the water in the basin, sloshing in a basin, it can't just be some stock prices. So you actually have to code up the input into a form that's acceptable to this computation. So you get this sort of commuting diagram like you see in homeomorphisms. But that's more or less what we mean by emulation. Again, the classic example. A Mac emulates a Windows machine because I can put in this code, which is, I think it's called soft Windows or soft PC, and then you give it the same inputs, you get the same outputs. Now, the reason I jumped to this fifth question about emulation from the fourth question is unpredictable. The thing is, you really need the idea of emulation to really express unpredictability. Because to say P is unpredictable means that if there's any Q that emulates P, Q takes just as long to compute the outputs. In other words, there's not some Q that emulates this that runs much faster. And the classic example of a computation that's not predictable is counting on your fingers by ones. So doing addition by counting on your fingers or by making marks by ones, I can emulate this. This can be predicted by regular addition using arithmetic. So if I have like 1, 2, 3, 4, plus 4, 3, 7, 9, I have this little algorithm that I learned in grade school for doing the addition, and I can get the answer, in just about, 20 steps, maybe 20 mental steps. And if, on the other end, I were to do this by saying, okay, well, I'll count up to 1,234, and then I'll count 4,379 marks past that, and then I'll look how many marks I've made on the piece of paper. I'll count them all, and that's how I'm going to do the addition. And that's the slow way. So this is a kind of computation that is predictable in the sense that there's a computation that does the same thing a whole lot faster. And one of the things we're going to be arguing in this book, or that I have been arguing, is that lots of naturally occurring computations are unpredictable in the sense that there's no quick way to predict them in detail. Now, we have our laws of physics, and they can give us a rough prediction of what's going to happen. But when you get down, you say, okay, well, look, where is this ball actually going to end up when I throw it into the room and it starts bouncing around? It turns out your physics equations aren't really going to help you. You're going to need to carry out a step-by-step emulation. So that was the thing in Section 2. Section 2, there was another thing that came up. I kind of threw a lot of concepts into that section. There were the four Wolfram's four classes. Or Wolfram's four complexity classes, if you want. And as I've said several times, we've got 1, 2, 3, and 4. And often 4 is the most interesting, but there's a sense in which 4 lies in between 2 and 3. 1 is the thing that just becomes constant. 2 is a computation that becomes periodic. 3 is something that's really messy. And then 4 is in between, where we have a pattern that's not repetitive, but it's not completely messy. And this is the zone that I often call the gnarly zone. Okay? And another, if you want to simplify Wolfram's four classes, and I could relate this to the question, relate Wolfram's four classes to just 3 kinds of computation. And what I sometimes, to make it like really simple, I talk about like a Red Riding Hood story. There's too cold, there's too hot, and there's just right. And what's just right is gnarly. Okay? So these are the too cold guys, class 1 and 2. Okay, so that's too cold. The gnarly, the lifelike, that's in the middle. And the too hot, in the sense of too complex, that's over here. Okay? What else is in section 1.2? Well, there's really a ton of stuff. The whole test could be on this section, actually. There's Wolfram's two principles, the PCE and the PCU. Okay. Well, before we do that, well, let's say PCE, PCU. So this is maybe question 7, question 8. What is the PCE, the principle of computational equivalence? And basically that says almost all processes that are not obviously simple can be viewed as computations of equivalent sophistication. And what Wolfram is saying there is essentially, if we leave aside one and two, these are the sort of obviously simple classes. And then he's claiming that all of these guys, the gnarly and the two hot ones, these actually all equivalent sophistication. Now, Wolfram didn't say what he meant by equivalent sophistication. You might say, does that mean they all can emulate each other? And that might be what he means, but there's some problems with that. I'll talk about that a little bit in a minute. One thing that's useful here in discussing this before we talk about PCU is what it means to say that a computation is universal. So what does it mean to say that P is universal? Do you all know that? What does it mean?
That P is a computation that can emulate any other computation.
Right. P is universal, can emulate any other computation. And before people thought very much about computation, it wasn't, it didn't even occur to anyone that there could be such a computation. And then maybe it wasn't obvious that there were any. But our friend Alan Turing, around 1930, proved that you can find universal computations. And then, as a little more time went by, people came to see it's not very hard for a computation to be universal. Because there's actually not that much goes into computations. It's more like just really, there's only a few things that they need to do. If they can do arithmetic, they can pretty much do anything. If they can add numbers, that's pretty much all you need. And so lots of computations are universal. So in a way, if we come back to the principle of computational equivalence, if you say anything that's not obviously simple is of equivalent sophistications, it's almost like you're saying that all these are universal. Now, there's a problem with this I hinted at before, and we'll talk about more later in the course. It turns out there are many computations that are gnarly and are not universal. Some guys proved this. Friedberg and Muchnick proved this in, I think it was the 60s. And now Wolfram's aware of this. What I think he argues is that, well, those are kind of artificially constructed things that Friedberg and Muchnick made up. These guys are weird recursion theorists. They have this complicated argument. And he said, well, those wouldn't actually occur in nature. That's kind of a weak position to be in.
Can a machine that is universal emulate one of those?
Yes, because a universe can emulate anything. Now, in CAs, we talked a lot about Rule 30 and Rule 110. And Rule 110, that's the one that makes these kind of moving gliders that bounce around. And as I said, Wolfram and Matthew Cook were able to show that Rule 110 is indeed universal, even though it's just a 1D cellular automaton. Now, Rule 30 is the one where we started out just with a dot. And you'll get something sort of regular on the left, but on the right, you'll get something that looks like the foam in a beer glass. And this is actually, it could be, this is a kind of a good example of a computation that's not obviously simple, but it might not be universal. It might be that it's just so seething and screwed up that you can't ever manage to propagate signals inside the foam and do something like a computation. So that's a fairly good candidate for being not universal. Okay. So as Wolfram stated, the PCE, in my opinion, might very well not be true. And later in Chapter 6, I talk about a weaker version that would be really just as useful. That probably is true. But my weaker version says that if you take any complex naturally occurring computation, it has an unsolvable halting problem associated with it of some kind. And it turns out I think that's likely to be true, and that gives us a lot of good consequences. The only downside of that principle, it's like the Polish Godfather. He makes you an offer you can't understand. I mean, it's hard to understand what it means to have an unsolvable halting problem. It's a complicated thing to define, and as many times as I've gone through it, hundreds of times by now, it's like a triple negation or quadruple negation. This prove that you cannot do, can't not. There's so many nots in having an unsolvable halting problem. It's a little bit hard to instantly wrap your mind around it. But we'll talk about that later. Anyway, something like the PCE, though, is an interesting idea. So saying that lots of naturally occurring computations probably are universal. And even if they're not universal, they're going to be so complex that there's going to be lots of undecidable formulas associated with them. Now, the other thing, this is something Wolfram didn't explicitly state. He sort of, in NKS, he almost sounds like he thinks this follows from the PCE, but it doesn't. And that's the principle of computational unpredictability. And I would formulate this as saying that most naturally occurring complex computations are unpredictable. And being unpredictable is a weaker notion than being universal. Okay, there's like Rule 30, again, example. That's fairly likely to be unpredictable. There's probably no way to speed that up. But it's not obvious that it's universal. So these are, and it's also possible to have universal computations that, because they're so slow and inefficient, they actually are predictable. Okay, so you can have. So the two notions are a little bit distinct from each other, but they're two interesting principles. And again, the upshot is probably a whole lot of naturally occurring computations are probably universal and unpredictable. Okay, so I go through that in section 2 there. And then in section 3, I give the example of arithmetic. So that's an example. We could even say, if I wanted an example, I could ask you to know that example. That doing an addition on counting by your fingers by ones can be sped up by addition using arithmetic. And it can be sped up what we call an exponential speed up. So it takes 20 steps to do this addition, but it might take, what is this? 1,234, 4,379. I want to add those. So that's like, that's like 10 to the 4th power, roughly. There's like 10,000 steps involved in counting by 1. And rather than using 10,000 steps to do arithmetic, you really just need to add 4 pairs of numbers. So it's like it's exponentially faster. Instead of doing 10 to the n steps, I'm doing n steps. So that's what we consider a really good speed up. Making something twice as fast we don't view that as, we say it's still unpredictable even if you do it twice as fast. It's if you can crush it and do it exponentially faster that we say you really, that thing is predictable. So anyway, that was that section. 1.3 was getting you to think about arithmetic that way. 1.4 was a little bit of a history of computers. And one thing that gets mentioned in there that's sort of important is universal is described a little bit more in section 1.4. Okay, universality. And universality comes up again because of the stored program concept. So I think it mentions von Neumann and the idea of a stored program. That was the kind of idea that sparked the coming of the age of digital computers. The idea being that a computer is, people began to realize it is this universal machine. And rather than reconfiguring the machine, I can leave it just as it is, but just give it a different program and it will behave differently. Okay, 1.5 talks about Turing machines. And this is, after all, a philosophy course, so I don't know. I'm not going to ask you the gory details of Turing machines. I'm not going to dig into that too much. 1.6 talks about how computers actually work. And I think maybe nothing too much I want to delve into there in terms of a test question. 1.7 talks about the network. Again, not so much. 1.8, though, gets into my great love, cellular automata. And this book's really just an excuse to talk about cellular automata. And I talk about some cellular automata here. And ones that I mention in here that are kind of classic ones. I talk about life. I talk about vote. I talk about brain. The details about brain are really in chapter 4, but I do mention brain in passing. We did demo. Then there's our friends Rule 30 and Rule 110. So it would be good if you had an idea of what these cellular automata rules are, how they work. If I was considering something I could do, if you look like on page 67, where they have these pictures that show how the rules are computed, where he has the sort of 8 cells, says the 8 kinds of neighborhoods, and then what happens. What I could do if I wanted, I could tell you that. I could say, okay, Rule 30 is based on these 8 transitions, and then I could give you a row and say, okay, let's mark this cell and this cell. Now tell me what the next 2 rows are using Rule 30. So you might practice trying to do that. It can be done. You don't have to roll your eyes. It's not that hard. You've got a universal computer in your head, right? But so you might, that would be, it's always good to have a question that some people can get wrong. Because, I don't know. Okay, another type of rule that I talk about a lot, I talk a lot about Belousov, Jabotinsky rules. And what do I mean by Belousov-Jabotinsky rules? Well, I mean rules that make pictures like on page 73. Okay? So they're the ones that make these nice scrolls that I'm so fond of. And this is actually, as much as Wolfram investigated CAs, he spent a lot of time on 1D CAs, and he didn't. It might have to do with the fact that he did most of his work in the early 80s, and it was harder to run 2 DCAs then, just as a practical matter. They're slow. But he doesn't say that much about Belousov-Jabotinsky rules, but to my way of thinking, they're pretty important. In Chapter 3, we talked a lot about these rules being important because they make biological-looking forms. And I think a lot of things in nature or in biology are related to these rules. Okay, and that actually gets us through with Chapter 1. So maybe, here's what I can do. I brought my digital camera, so I'm slightly electronic today, but in a different way. So I'll take the reason I have my camera is my daughter's visiting with our granddaughter. So I've been taking lots and lots of pictures of the baby. But I'll take pictures of this, and then I can erase it, and I can even post this, see? This is what they do sometimes at companies now. People have sort of gotten tired of PowerPoint. So what they'll do, they'll have the engineers just work on a whiteboard and then post the whiteboard to the web. So that's the sort of easy way to do. Yeah, I guess that looks sharp enough. Looks better without flash, I think. So now, huh?
I saw it on your bill LCD screen. Flash was putting in glare.
It did do some glare with the flash. But maybe we better shoot this one without flash. Let's see. That one looks good. That one looks good. With the issue without the flash is these cameras, they weigh about an ounce. And it's easy to have them shake while you're doing it. Gee, this is going to be a long test. But I'm not going to ask all these questions, right? But so we've got 14 questions here. So we'll erase these boards, and then we can start over. Bring what? No, I don't think we'll do blue books. I could maybe bring some paper for you to write on. Maybe I'll do that. That's what I usually do, bring up a bunch of paper, and if I can get into the math office and get some. And I think we'll just do an hour rather than, letting it drag on and on. And then probably I'll have my new story done by next week. And so then, after the test, then I can read the story to you as a treat. Though maybe you'll be angry at me. Maybe I should make you listen to the story first. Okay. So question number 16. Okay, that brings us into Chapter 2. And Chapter 2 is about physics, and huh? Oh, I thought I had 15. Wasn't 15 Belousov-Jabotinsky? Huh? That was 14 was Belousov-Jabotinsky? Okay. So 15 is going to be analog and discrete. Because that's the sort of one of the first issues that comes up if you say physics is a computation. People say, well, then physics is analog, computers are digital, so the computers we know can't be doing it. And my way around it is this definition I have. I said it's a definition to smooth the difference out and just say a computation is digital if its states range over a small set of discrete possibilities, and it's analog if it has a very large number of possible states. And I don't say infinite, okay? Because if you say infinite, then you're off in the la-la land of pure mathematics, where I'd like to go there too, but right now if we're saying everything's a computation, it's more realistic to say the things we call analog really just have a lot of states. So this would be how to resolve that problem. Now, I talked about continuous valued cellular automata. Okay. Continuous valued cellular automata, meaning that what I'm going to put in for the states, instead of it just being single bits, I'm going to put in real numbers, which, yeah, floating point numbers. So I'm using continuous in the computer science sense of the word, not in the mathematical sense of the word. But again, we've always got this thing, look, if you go out to 10 to the minus 30th meters, or whatever it is, you're running into the Planck scale, and lengths don't really mean much out there. So maybe if I got a 64-bit number, maybe that's enough. So there's four things. The CA architecture, and this is like on page 89. It's the idea that this is this architecture that we have in cellular automata. That's also what we call the physics architecture. And there's five properties of it. Okay, you have many processors. There's one shared memory. So there's locality. Each processor has access only to its local neighborhood. Homogeneity. Each processor has the same rule. And synchronization, the processors run at the same speed as one another. And this architecture, you can either apply it to CAs or you can apply it to thinking of the world as a bunch of particles. These are sort of dual ways. It's like the old particle-field duality. CAs are more like thinking of the world as made of fields and particles. But if you have particles, you could say, well, the particles are the processors. The shared memory is this space-time that they're in. Locality, they just interact with what they bump into. Homogeneity, physics is the same everywhere. Synchronization, they've got the same clock. So either way, but it turns out, in terms of doing computer simulations, you can get nicer things happening more easily with the continuous valued cellular automata. And a couple of rules. The wave rule, and that's the rule nu C equals C plus neighborhood average minus old C. I think sometimes I've written this wrong on the board. I think sometimes I've forgotten to put the C plus in here. Okay? So if this cellular automaton rule, which it does a really good job of modeling wave motion in space, which seems like something pretty complicated. So for each cell, we track three values. The cell's current value, C, the cell's current value, old C, the former value, old C, and the new value, new C, that we want to compute. New C is gotten by taking C plus the neighborhood average minus old C. And the reason, one way to see that this is the right formula is new C should be roughly the same size as C. And the thing is, these numbers, all four of these numbers here, ought to be around the same size. Okay? There's just some quantity in all these cells. We're averaging them all the time. So these two kind of cancel each other out. Okay? So if your neighbor, notice if nothing's happening, if your neighborhood average is the same as the old C, these cancel each other out, so new C equals C. So that's why you need the C here. If you didn't have it, these two sides wouldn't be roughly the same size. And as I say, this rule works amazingly well. And I've done this in 1D, I've done it in 2D, I've done it in 3D. I haven't done much with it in 3D, though, because it's hard to see three-dimensional cellular automata. And the kind of average you do, actually, the rule isn't even that sensitive to it. One way to average, you could say, well, just take my four, if I'm in a 2D CA, I could say, well, just look at these four cells and average them. That's like a fast way to do the average. Or you could say, let's look at all nine cells and average them. You could do that too. Or you could say, let's do a weighted average and weight these a little bit more because they touch the center, and weight these a little bit less. And you can do it that way too. And whichever way you do it, you will get something that looks like a wave. But as you do, people that do mathematical physics or let's see, want to do very exact computational models, they can get into analyzing this. And it turns out there's different ways to take the average that make it work more physically or less physically. Anyway, that's the wave rule. And the other rule, the heat rule, is even easier. The heat rule is simply nu C equals neighborhood average. Actually, if you do that, it converges a little too fast. So what we tend to do is nu C is usually write it as 1 minus A times C plus A times neighborhood average. And this number A here, that's my diffusion rate. And if the diffusion rate is 0, then nu C is just equal to C, and this drops out. If diffusion rate is 1, nu C is the neighborhood average and diffuses as fast as possible. And you can crank A up and down and let things diffuse either more rapidly or more slowly. And you need that ability. When we want to model, in biology it's important, and in physics, and to model how rapidly it spreads. There's also, for that matter, coming back to the wave rule, I can put a number lambda here, and this can control how rapidly the wave moves. In some sense, lambda is the speed related to what you'd call the speed of light in this space. So if you make lambda you can crank the speed of light down or turn it up, and you'll see the waves moving either faster or slower, depending on the lambda you put in. Okay. So those are some specific CAs I got into. I had some pictures of some nonlinear CAs. A nonlinear CA, you could say, instead of having this, I could put an exponent up here. Like I could put a squared here or cubed here. The cubic wave equation does some really nice things. Well, nice in terms of being really, really gnarly. Okay? So you could put an exponent here and make a wave be nonlinear. But let's not worry about that. Let's just put a question mark there. Okay. Now the next section, 2.3, we got into chaos. And I had this thought experiment, chaos in a bouncing ball. And I made the point here. Let's see, how could I put this into a question? We talked about this idea about dropping a ball on something. About half of them go to the left, half to the right. So I guess, how can we say the Venn experiment is deterministic? Okay, so that's kind of the question there. That's how can we argue that if I drop this ball on this divider in a bin and it ends up on the left, it ends up on the right, so how can you say it looks probabilistic, so how can you say that it's deterministic? And the way I argued it, there were two angles that I used. One angle was that the ball's starting position is, your chance of starting it in the exact same location is minuscule. Okay, I won't quite say that it's zero probability, because if space is quantized, then you would have some chance of hitting the same slot in space again. But it's very, very, very small, okay, like 10 to the minus 30. You could do it for a long time and never hit the same spot twice. You could do it for all the time that there's been in the universe. So that's one reason you could say it's deterministic, but the idea is the inputs are never the same, to make a long story short. Because there's the starting input is never the same. And then there's the fact that we're not in a vacuum. The ball is not the same. You never drop the same ball twice. Because once the ball bounces, some stuff gets chipped off it, stuff sticks on it. You never pick up the same object twice in your whole life. Every time you pick up, huh? No man steps in the same river twice. And no man, no person, no woman, no man shops and fries but once. Because you always get the wrong thing. You always have to go back.
It's always 2 trips.
It's always 2 trips to fries. Yeah.
That's not as bad as the plumbing store.
The plumbing store. I have a lot of trouble with plumbing. I just can't do plumbing. And it's hard to find a plumber, too. It somehow seems harder than finding, like, a painter, electrician, carpenter. Those somehow are easier. I don't know. Anyway, maybe San Jose State should open a plumbing department. Help our enrollments. So the inputs are never the same. And also the other thing, coming back to this question, is there's what I sometimes call the extra inputs, or the interactive inputs. And these are the air, okay, the electric fields, just the magnetic fields. There's just other little trifling things that get involved. And you can't control those. So it can be deterministic, but it's never the same. And that's typical of chaotic processes. And so basically, a computation is chaotic. A physical computation is what physicists call chaotic. If what? And one simple way to say, if it's sensitive to variations in input. And there's actually some other things that go into the formal definition of being chaotic. Not only is it sensitive to variations in input, if you have a chaotic process, it has this thing that it will sometimes settle down and look periodic for a little while. Okay, so that's something else. So lots of computations are chaotic. They're very sensitive, but they can look. Another thing about chaotic things is there's different levels of chaos, and that's something I actually get into, I think, a little further on. That many chaotic systems do have strange attractors. There's zones that they hang around in. They're not really random. Okay. But coming back to this section, here I bring up the principle of computational unpredictability again, and I give the example of a projectile. Then I have a section called the meaning of gnarl, and here I'm getting into the idea of what Wolfram calls intrinsic randomness. Okay, so this would be what is intrinsic randomness, and that's the property that many computations have of being unpredictable. Really, it's really another way of saying unpredictable, but it brings in the fact that some computations, like again our friend Rule 30, or for that matter, let's stick with Rule 30. Some computations, even with exactly fixed, simple input. So with the ball experiment, really, you could say, well, maybe all the interesting gnarliness that you're seeing just has to do with the fact that we can't drop the ball in the same position. And the thing is, what happens when you get to intrinsic randomness, this pushes it back. It says, well, actually, that's not true. I can have things where I have exactly fixed, simple input, and the output is gnarly and random looking. And the reason is simply that's what the computation does. The computation, Rule 30, it munges on itself. It just is generating, spewing out this random looking data, even though you gave it a very simple start. And water is an example of that, where you can set water to flowing and it will generate these very complex looking patterns that don't have to be because of variations in what you put into them. It would do it the same even if you could reproduce everything. So that's what I get into in that section. Then we have the quantum mechanics section, which well, one thing, the big problem with quantum mechanics is if we have, if quantum mechanical events are fundamentally unpredictable, then that seems like that violates universal automatism, because then we've got something non-deterministic. And so I might not ask you a question about this stuff, because I always feel so unsure of myself when I talk about quantum mechanics. But you could say, how to evade the seeming non-determinism of quantum mechanics. And one way is many universes. And there's another way, which I didn't explain all that well, which is called the transactional. Basically, it's having future effects in the past. Okay? So these, it turns out there's, and yet another way might be there's smaller stuff. So there's three ways to evade the seeming non-determinism of quantum mechanics. One way is to say, well, it is deterministic, both outcomes happen, and it just happens to look to us in this universe that only one happened, but there's copies of us in another universe where the other option happened. So it's like if we have a choice tree, or we're making like lots of yes-no decisions, we could say, well, our history is this one path through the choice tree. Now, if only this one path exists, then you say, well, why did history turn out this way instead of being all these other ways? And the traditional Copenhagen interpretation of quantum mechanics sort of wants to say, there's no reason for it. It just happened that way. And yes, it's incomprehensible, tough luck. And, you know, that doesn't satisfy me. So I could say, well, maybe every branch happens. And so then there's nothing to explain. We say that this is just this whole continuum of all the possibilities. You then say, well, why does it feel like the history's like this? Then you say, well, look, there's also a guy over in this universe here, and this person is saying, well, history was like this. So each person in each parallel universe will have their own notion of history. Yeah?
Yeah, so you also seem to be saying, which is that the Copenhagen interpretation is in contradiction to everything in computation.
At least the way that I understand it, because it seems to say, I mean, if you take, I have this quote from Feynman in there, and if you take him at his word, he's saying there's absolutely no underlying reason why, you know, you measure something, you get a 0 or a 1, and it doesn't even make sense to ask why did you get the 0 or the 1. It just happened that way. That's a brute fact. There's no explanation for it. And so that's non-determinism. Oh, B is the future affects the past. That's this thing called the transactional interpretation of quantum mechanics. And see, you might say, when we, again, going back to the bin experiment, dropping the balls, we said, well, look, there's this data you didn't notice, the exact position of the ball, the chip on the ball. There's more hidden variables that determine whether it bounced to the left or the right. And some people have said, well, maybe each photon or electron has a bunch of data hidden inside it. It's got these hidden variables, and that's determining whether you get the 0 or the 1. Now, they've devised some real sophisticated experiments to show that simple notions of hidden variables don't work. You can do experiments that show that you can't just say that there's a bunch of data in each photon that determines what happens. For reasons that I won't go into, that's not going to work. But again, that same analysis is it's okay to have hidden variables as long as some of your hidden variables are in the future. In other words, if you have reverse causation, then hidden variables are okay. So it's like hidden variables, you can have them, but they're expensive. You have to break something else in physics to have hidden variables. So I want determinism, I want hidden variables. So I have to break something. One thing I can break is causation. And it turns out if you allow signals that go backwards in time as well as forwards in time, then you can have your hidden variables in some sense, and you can have determinism.
So is that a version of the universe we have is the one that's kind of interesting in the sense of the outcome?
Not necessarily. I think you're talking about the anthropic principle, maybe.
Well, yeah, a little variation.
Or sometimes people say there's many universes. Why is the one we're in so interesting? Well, if we weren't here, it wouldn't be very interesting, Or it's like, we wouldn't be here asking this question if we weren't in a universe that had us in it. So and that's
There's actually many more interesting.
Yeah, there might be ones with even more interesting things. But now, one thing I need to warn you, the trail of logic connecting, allowing hidden variables to get rid of determinism and to having the future affect the past, there's a lot of steps that I'm skipping there. Like why if this, why that? And I'm not telling you why. Mainly, I don't know why very well. I mean, I've looked at the arguments and I can follow them, but I don't know them well enough to teach them and explain them really well. But that seems to be an out. So, and actually Ephraim, when he does his paper on entanglement, he can tell us more about this. You can read up. I'll keep adding to his reading list.
Yeah, we need to talk about it.
We need to talk. Okay. Okay, we can talk in the second half. It's almost time for the break. The third way out of quantum mechanics is to say, well, look, quantum mechanics isn't a final theory. This is what Wolfram likes to say. He says it's like when people were talking about pressure and temperature as if these were fundamental properties of nature, and they didn't even realize that it's statistical mechanics. Like temperature is an average velocity of the atoms, and pressure is the number of the atoms. And so it's like there's all this stuff under quantum mechanics that we haven't gotten to yet. And there's some motion in that direction in physics too. People talk about digital physics and spin networks and quantum loops and little strings that are tied up. And maybe that would be another type of stuff that's maybe then that it would be deterministic. There would be a reason why the photon does this or that. Okay? So, in other words, I don't think quantum mechanics at present, it seemed maybe to be in a stronger position about 10 or 20 years ago. But I think now we don't necessarily have to accept that it ruins determinism. Okay, so that's the end of Chapter 2. And there's still some questions about Chapter 3. But at this point, I think we're ready for a break. So let's take a break for 15 minutes. So let's do a few more test questions. Let's see, this would be 22. So this gets us into chapter 3. So what is life? So it's the thing life is self-reproduction plus morphogenesis plus homeostasis. And then life leads to ecology and evolution. So the idea in this chapter is to try to, what's the last one? Evolution, homeostasis, morphogenesis. So there's really 5 different things that we can talk about in terms of in computations. And one idea worth mentioning is what I mean by saying that DNA is a tweak parameter. And again, what I meant by that was that DNA does not have a blueprint for how your body's going to look. What it does, it controls certain parameters in a naturally occurring process that will lead to your body growing. But it doesn't, it's not down there at the pixel level, you know. Morphogenesis, I have a little more to say about. And this gets into the idea of what is a reaction diffusion rule. And that's a rule you can think of as a cellular automaton. And we have diffusion, where the neighboring cells, cellular automaton, and we have some quantities that are in the cells, and Turing called these morphogens. Okay, a morphogen meaning something that changes your form. And the morphogens, each cell normally has more than one morphogen. And the morphogens do 2 things. They diffuse one cell to the other, okay, like these chemicals go from one cell to the other. The other thing is that they do is react with each other. And the reaction, one type of reaction that you see a lot, is activator-inhibitor. The morphogens can interact with each other in various ways, but we often see pairs of morphogens that are activator-inhibitor pairs. And where one activates some process and the other inhibits the creation of the activator. And what we found, what kind of patterns these can make, what kind of patterns can you get, or what are Turing patterns. And you can get dots, stripes, filigrees. If you think in terms of 3 dimensions, you can get bumps, striations. Okay. And also, we can get our friends, the Belousov-Jabotinsky scrolls, which, it's sad, but I think it's true. You don't see many animals that have Belousov-Jabotinsky scrolls on their hides. I guess these scrolls that I want to say about, the Belousov-Jabotinsky scrolls. Now, these reaction diffusion rules can create these nice scrolls. I mean, why don't you see that in nature? You always just see stripes or dots. You could be seeing these.
Maybe there are those things that get stopped at some point. Go on.
Well, maybe, or there is. I did a lot of experiments with reaction diffusion CAs, and I did find that there's this sort of range. If you look on page 166 and 167, it turns out you only get the scrolls if the activator inhibitor spread at about the same rate. And generally, if the activator spreads much slower than the inhibitor, you'll always end up with spots or stripes. So it might be that for whatever reason, in biological systems, the things that activate the color change. Why would they travel slower than the inhibitor? Well, if they're bigger molecules, it might be like big, complicated molecules that travel. Huh?
I mean, could you ask the same question the other way around and say, why are there spiral galaxies instead of forming in cubes?
Let's do, why don't we have the Milky Way polka dots, or the Milky Way stripes. The things that work in forming the spiral galaxies, it's not exactly an activator-inhibitor process, I don't think. Oh, that's true. It might be. Well, I think if you want to be camouflaged, being camouflaged with stripes, would spirals be worse as a camouflage? I don't know.
Yeah.
I guess it would.
Right. I mean, it may be just an initial condition.
Yeah, I mean, what happens, again, DNA is this tweak parameter, and it would be something like controlling the rate of spread of the activator that's in your system. And that could get cranked up and down. The specific pattern of stripes wouldn't be controlled, but yeah. Yeah, it might be that, maybe, I don't know. I'll have to think. I bet if you root it around, you could find something in nature that has spirals on it.
Well, there are some plants that mathematicians always love to talk about.
Oh, the sunflower seeds, yeah. See, the sunflower seeds, they're in a spiral, but that's not a Jabotinsky spiral.
Maybe there's something wrong with your
With my line of thought.
the prediction is making don't seem to be turning out.
Well, it's food for thought. That's an open question. You can research that for me. Okay. Anyway.
Is that question 25?
Oh, actually, what am I saying? What am I thinking about? We've got scrolls all over the place in our bodies. I mean, take a slice of your brain. I mean, that's totally those scrolls. Or most of your tissues. Your brain in particular. A fetus is a little Jabotinsky spiral. Right? Well, it's a 3D Jabotinsky spiral. It looks like this. Here's a little eye, little hands. Okay. So, yeah, of course, for some reason, it doesn't get used for skin patterns. Okay? It doesn't seem to be used for skin patterns, but it is being used for the shapes of things.
Yeah, and you do get it in horns. I mean, you get it in horns, but not
Right, horns, good point.
in skin patterns.
Yeah, horns do the spirals as well.
I mean, the only thing you get is, they say, the hair itself travels around in a spiral. Human hair.
Yes.
Out of spiral.
Yeah, hair spirals.
But you have to go to your, look at your hair spiral.
Yeah, you get the Jabotinsky curl. I talked about homeostasis a little bit. I don't think there's a good question I can draw from that. I talked about the chaotic growth. That's sort of an interesting thing. I talked about the logistic map. That would be an idea of a chaotic population size arising from the logistic map. So I could maybe ask you a question about that. The thing, let's see, evolution, that was the last section of the chapter. That was section 3.6. Just a couple of things to notice that for evolution we need, we kind of need three things. You need a genome, artificial life, yeah. I don't think I'm going to ask any question on artificial life. I don't think I have a good question on that. but the last section, to get evolution, you need a genome, you need variation, and you need selection. Right. And then there's some stuff I talked about. Evolution as search, okay? As search in a fitness landscape. Okay? And one thing we discussed was that it's very hard to find the best point in the fitness landscape. And there's been people that argued that means evolution doesn't work because you can't find the optimum point. But the point to remember is you don't need to find the best point in the fitness landscape. You just need to get your head above water. Okay? Just be a little bit ahead of the game and you'll be okay. So, yeah, maybe that's enough. Let's stop at that. I'll get a picture of that. We'll be done. Trim this off.